Hi everyone, I am M. Seshagiri, Department of Electrical and Electronics Engineering, Vardhaman College of Engineering. Today, I am trying to explain about the experiments. So this is Electrical Machines 1 lab. In this, the very first experiment is magnetization characteristics of a DC shunt generator. So I request the students to verify the earlier video made by me about the introduction given for this electrical machines lab, including the demonstration kits where I explained each and every part of the motor with working principles and the controlling panel from where we are getting the power supply, DC power supply, AC power supply, and AC also we have single phase and three phase power supplies. As the syllabus includes with only DC motors, we are successfully using the DC power supply supplied by the control panel where there is a rectifier. From that rectifier, AC is converted into DC. That DC is taken at the main panel. From there, each and every individual panels are supplied with the DC power supply. So that video already made earlier. So that will be explaining about the power supply distribution in this laboratory. So we focus on the today's experiment, which is magnetization characteristics of DC shunt generator. For this, we need a motor. Generally, to explain about the working principle of a DC shunt generator, so there is a principle, Faraday's laws of electromagnetic induction states that when conductor rotated in the magnetic field, so due to the change of flux, EMF is induced. So to move the conductors in between magnetic field, we need a prime mover. So generally in outside area, the prime movers are by means of tidal energy, water energy is converted into mechanical energy. From that free natural sources we are taking and thermal energy, nuclear energy, wind energy, like that. All together we cannot bring it to the laboratory. I have only one source, which is motor. So a motor is mechanically, this is the DC motor and which is mechanically coupled to the generator. So this coupling arrangement in this section. So when I start the motor is a device which converts electrical energy into mechanical. So since the shaft of the motor is coupled mechanically to the shaft of the generator, shaft is nothing but the conductors. In between magnetic field it is moving. We are making conductor to move in between magnetic field by taking the mechanical energy of the motor. So like that, when conductor moves into the magnetic field, due to the change in flux, EMF is induced. So amount of induced EMF depends on the rate of change of flux. As much flux it will change, that much voltage is going to induce in the generator. So in this experiment, in this particular experiment, we are making use of electromagnetic field coils. That is, when current flows through any iron wire, metal, it's not bad. So when current flows through any iron metal, the molecules arranged in the iron metal will be in random position, but the DC current which is applied to the iron piece will make the all molecules to arrange in the sequence mode as in a magnet. So thus the magnetic property induced in an iron piece. So that type of electromagnetic field coils we are making use in this particular generator. So that is represented with ZZZ in the generator section. And the coil which is rotating in between magnetic field is represented with A and AA. Generally we refer it as armature terminals. Generally we refer it as magnetic field coil terminals. So this is the generator section. When coming to the motor, same magnetic field coil, same armature current, armature coils and DC power supply which is given as input to the motor. Once motor will get started, the generator coil also rotating in between magnetic field. The field flux is controlled by a rheostat which is connected in the generator section. So initially we will keep it in maximum position. Slowly we will vary the resistance. That means we are decreasing the resistance, allowing more current to flow through the magnetic field. That increases the amount of flux. As the amount of flux increases, the change in flux also increases. As the change in flux increases, generated EMF also increases. That we will observe by this experiment. How EMF varies with the variation of the flux. So flux is nothing but related to magnetic. So This experiment is called magnetization characteristics. How much magnetization you are providing, what is the voltage induced in the generator. That is the experiment. So for that you need to know the specifications of the motor and generator. Then only you can operate the resistance currents within the limits of this specification. So motor, generally it is a type of motor is shunt motor. Rating of the motor is 5 HP. Speed of the motor is 1500 RPM revolutions per minute. Voltage is 220 volts. And the current rating of the load can be applied on the motor. Maximum current will be 18 amperes, 18.5 amperes. And the excitation current which is given to motor side is 220 by 0.95 current. This is about motor specification. One should write these specifications under the circuit diagram in the manual. So next, coming to generator, we should know what are the operating voltages of the generator, what voltage, up to what extent voltage can be induced in the generator. So for that, the type of the generator is shunt, and the rating of the generator is generally DC generators or DC motors are rated in, DC generators are rated in 3.5 kilowatt, and speed is 1500 RPM, voltage is 220 volts, current is 16 amperes, and the excitation, this is very important, 220 volts by 0.48. So generally we know the R equals to V by I, where V is 220 and I is 0.48. So the range of the resistance depends on that voltage by current rating. If you divide that quantity, it will be coming around 470. So the range of the resistance should be more than 470. Then only we can obtain the rated voltages, generated voltages in the resistance. So this is the excitation rheostat, and it is rated for 600 ohms by 1.7 amperes. 600 ohms by 1.7 amperes. It is a variable rheostat. By varying this, you can increase and decrease the resistance value which is connected in the magnetic field coil. So by varying this, you can control the current flowing through the magnetic field coil. So I have selected this 600 ohms of resistance since my excitation current is 0.48 and the voltage is 220. R equals to V by I, 220 by 0.48, it coming around 470 ohms. So I have selected more than that 470 ohms, that is 600. In this way, we will select the range of the rheostats. And the voltmeter which is given as this line indicates that moving coil instruments which are used to measure the DC voltages. Moving iron is for AC voltage, moving coil is for DC voltage. Since the generator is DC generator, so I have selected the voltmeter as moving coil instrument which will measure the DC voltages, and the range of this meter is, you can see it is 600 volts and 300 volts. The dial belongs to 300 volts, and you have separate terminals, voltage terminals for 600 as well 300. So here the voltage, generator voltage is 220 volts it is given. So 300 voltage terminal is enough for us. So 300 voltage, directly the reading which is showing by the needle, we can directly take the voltage value. If you select the 600 terminal, the deflection should be multiplied with 2. So in that way, we will take the readings of the voltage. Anyhow, we are connecting to 300, so whatever the deflection, it is direct value, we can note it down. And moreover, I need to know the field current which is connected to magnetic field coil, that is ranges to 0 to 1 and 2. Two options are given, 0 to 1 ampere, 0 to 2. This is also moving coil instruments which is indicated with a line. So if the line is there, this is definitely, it is for measurement of DC. Since our excitation current already we have seen 0.48, so I need to take 1 ampere of current. So this terminal I will connect in the magnetic field coil. So as I am varying this rheostat, the current also varies. When the current increases in the magnetic field coil, it increases the amount of flux. As d phi by dt, amount of flux, change in flux will vary as the voltage also increases. So gradually increasing different currents within the range of 0 to 0.48 for different phi values we will note down for every step of current, we will note down the voltage induced in the armature terminals. That is the experiment here. After obtaining the values in increasing mode as well as in decrease mode also you have to take. So slowly we will increase the currents to 0 to 0.48 value, and after reaching the maximum value we will again decrease the same values to 0. In the decreasing mode also we will take down the voltages, increasing as well as decreasing. After taking these voltages, we will calculate the critical field speed and critical field resistance. Two quantities we need to know by conducting this experiment. The aim of this experiment to understand the magnetization characteristics of the DC shunt generator. Since it is not connected to load, we can refer it as open circuit test also. Now we will see how to connect the circuit. Explain briefly about the circuit diagram. So here you can see the circuit diagram. One is motor section, the other one is generator section. In motor section there is a starter L, A, Z. So here L, A, Z, these three terminals are belongs to 3-point starter. Since the DC shunt motor is operated with the 3-point starter, so remember one thing, power supply is directly connected to L, plus is directly connected to L, and after that Z is connected to rheostat to control the speed of the motor. This rheostat is essentially required. So if it is rotating below rated speed, by increasing this resistance we can increase the current in the magnetic field coil, and here we understood that the current increasing in the magnetic field coil increases the generated voltage, but coming to motor side, if the current decreases, speed will increase. Vice versa application. Motor is different and generator is different. In generator section, current increases, voltage also increases. But coming to motor, if current increases in the magnetic field coil, flux increases, speed will decrease. In order to increase the speed of the motor, you need to decrease the current, decrease the flux, increase the speed. The relation is N is equal to EB by phi. Flux is in denominator, so when flux decreases, speed increases. So reverse manner. So now let us see how to connect the circuit. With the help of Madhu sir, I will try to connect the circuit. I will explain the connections. He is going to connect. So first take positive terminal and connect it to L. Slow. This positive terminal taken to L of the starter, right? Next, coming to magnetic field coil Z, there is a Z starter Z is here, and it is connected to rheostat one terminal. So take 400 by 1.7 rheostat, and already terminal is connected. So Z is taken to rheostat, and rheostat other terminal, there are two terminals here. This position indicates if it is near to terminals 0, if it is away from the terminals maximum. So now the resistance point is 0. If you keep this knob at the initial position near to these two terminals, it is 0 position. And the next terminal of the rheostat is taken to motor Z. This arrow mark is connected to motor Z. Now A terminal of the starter, A terminal A to A, this A to A. Next, AA terminal is connected to ZZ and negative. AA to ZZ and negative. So now this is connected to, AA is connected to ZZ, ZZ is closed at negative portion. So we have not connected any meter in motor section because our experiment is connected to generator. All the meters are connected at generator. Anyhow, we have a display for voltmeter here. We can get the display of the voltage here, and this is internally connected. This reads the speed of the motor in revolutions per minute. The speed of the motor is sensed by the switch. You cannot see it. Backside of the motor there is a proximity switch. Proximity switch will sense the rotations and displayed in this meter how with what speed it is going to rotate. So our speed limit I already seen in the name board, that should be 1500. We will reach 1500 speed by here. If it is rotating below rated speed, let us say for example 1400. So I explained you, when you decrease the current, flux decreases, speed will increase. So it is at 0 position. To decrease the current flowing through the magnetic field coil, I have to increase the resistance. Resistance increase and current also current decreases because resistance will oppose the flow of current. So when current decreases, flux decreases, speed will increase. In that manner, we'll take the motor speed to 1500 rated speed. So after updating rated speed, now generator connections. So you can see A and AA, armature terminals, these two, and magnetic field terminal ZZ here. Generator connections. So everyone knows that voltage induced in the armature terminal. So initially I'll connect a voltmeter across A and AA, connect it to A, and 300 terminal. You take this 300 terminal and connect to AA. Even it is an iron piece, it is not magnet. The current makes the iron piece to behave like a magnet. Initially, it is having a residual magnetic property, inherent a small amount of magnetic property in the iron piece. Because of that, a small amount of flux will be releasing. Even though there is no current flowing through this, because of that residual magnetic property in the iron piece, a small amount of voltage initially induced. That is the reason in this experiment you can see graph will start little above from the voltage value. Initially only at 0 position only the voltage will be inducing because of that residual magnetic property. So the induced voltage, we are taking that same voltage connected to magnetic field coil. Instead of external DC source, we are connecting the same induced residual voltage connected to the magnetic field coil. That is going to increase the magnetic flux in this magnetic field coil. So I will connect, that current is to be controlled, so I will connect a rheostat between this voltage and magnetic field coil. That is reason. So I have taken this 600 ohms rheostat. I already explained you the amount of the excitation current is 0.48 and the input voltage is 220. 220 by 0.48 gives above 400. So I have selected 600 range. And this is initially connected to this voltage. So the input voltage, the induced residual voltage will flow to the magnetic field via this rheostat. So initially I'll keep the rheostat position away from these two terminals, that means maximum position. And then this is to be closed and I want the field current, how much current I am going to apply in the magnetic field. So I will connect an ammeter here. So since the range of this excitation current is 0.48, I need not to go for two terminal, I will connect it to one terminal only. This is closed at armature, AA. So which is shown in the circuit diagram, it is very clear that ZZ is connected to ammeter, ammeter other terminal is taken to AA. Thus the circuit is closed. So this is about the connection diagram. Now let us verify. As I have already explained you, I will start the motor. When the motor gets mechanical force, that is given as input to the generator, which is going to move the coils in between magnetic field. As conductor moving in the magnetic field, due to the change in magnetic field, the voltage is induced. The amount of voltage induced depends on the rate of change of flux. Rate of change of flux depends on the current flowing through it, and the current is controlled by this rheostat. I will show you practically. So let us switch on 10. కొంచెం ఇక్కడ జూమ్ చేయాలి మీటర్ల దగ్గర వోల్టేజ్ వచ్చినప్పుడు కరెంట్ వచ్చినప్పుడు ఈ కరెంట్ని ఇది జూమ్ చేసి చూపెట్టు. ఒక్కొక్క స్టెప్ పెడుతుంటా కరెంట్ చూపెట్టాలి, వోల్టేజ్ చూపెట్టాలి. కరెంట్ ఇది ఇది ఇక్కడికి లిమిట్ 0.4 వరకు. ఇది వోల్టేజ్, ఇది 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 నేను వేరీ చేస్తుంటే ఫస్ట్ కరెంట్ చూపెట్టాలి, తర్వాత ఇది ఎంత మూవ్ అయిందో ఇది ఎంత మూవ్ అయిందో చూపెట్టాలి. ఇప్పుడే ఫోకస్ కాదు, ఇప్పుడు నేను ఫస్ట్ స్టార్ట్ చేసే మెథడ్ చూపెట్టాను, తర్వాత అటు ఫోకస్ చేసుకోండి. సో నౌ we will start the motor. So this is the MCB. I already switched on there at control panel for the panel number 10, and this is the AC supply which is given for the display of this motor. So I'll try to explain this. So MCB is switched on, and now I'll switch on the, keeping this at minimum position. Always remember, motor rheostat, always you keep it in minimum position. Generator rheostat, always you keep it in maximum position. That is the precaution, utmost precaution we need to take. So now it is switched on. So slowly rotate the starter and observe the motor is rotating. That motor is rotating at the speed of 1424 RPM. So we need to set the motor speed to 1500. So I already explained you, if you decrease the current, speed will increase. So decrease of current possible with the increase of resistance. So I am increasing the resistance in the field coil. You can see current speed also increases. Like that, you take the speed of the motor to 1500 RPM. So it is at 1494. So approximately it is exactly 1500 speed. So after setting 1500 speed, now you can observe, I already explained you, there is a residual magnetic property. Because of that, I kept it maximum position. It doesn't allow any current to flow through the magnetic field coil. There is no flux as understanding. But because of the residual magnetic property, there is a small amount of flux will be there. By changing that flux, initially your voltmeter already reading here. You can see it is above 26 volts initially it is inducing because of the residual magnetic property. The voltage never starts from zero in this experiment. So the reason is your magnetic field coil, which is this electromagnetic field coil, iron piece possessing a residual magnetic property. So magnetic property is there, so little amount of flux is induced. By changing that little amount of flux, initially starting with 25 volts. This voltage is taken by this wire to the rheostat. Entire resistance is taken and leaving from this black terminal to Z. That means the current flowing through the magnetic field coil is controlled by this rheostat. So your ammeter is very negligible current, 0.02 current. So I will vary this current so that current flowing through the magnetic field increase and the flux increases. As changing flux increases, voltage also increases. Now please show to the ammeter as well as voltmeter simultaneously. So I will increase the current. You see the current is increasing. The needle is moving on current. As current is increasing, the voltage also increases. So our limit is, it should not exceed 220 volts. It should not exceed 0.48. So like that we will take 4 to 5 different values by varying current. It is already at 0.3. So our limit is 0.4. So at 0.4, the voltage induced will be maximum. Maximum voltage 220. So by increasing the current, we are increasing the amount of flux, and change in flux changes and the voltage is also increases. This is the increasing manner. Same experiment can be carried out in a decreasing manner also. Whatever the points of current we have noted down, same points you keep here and note down the voltage decreasing. So like this, increasing values as well as decreasing values. There is a slight difference between increasing and decreasing. So that you can observe from this graph. So increasing mode and decreasing mode. Voltage value taken on this axis, current value taken on IF, field current is taken on this X axis. So by plotting the graph, you need to take the slope of this graph to obtain resistance, critical field resistance. That is the experiment. So connected to this experiment, there is another experiment which is load test on DC shunt generator. So we have not connected any load to the induced voltage, but in the next experiment we are adding one rheostatic load box here, and we are keeping that rheostatic load box to the induced voltage and slowly varying the load and observing the voltage value and current value. That is next experiment connected to this. Entire process is similar for the second experiment, which is shunt load test on DC shunt generator. Only the thing is, induced voltage side we kept it as open circuit, but in that experiment we connect a load and test the performance characteristics of DC shunt generator under the load.